In a quiet corner near Mianyang, China is building what might be the most ambitious sun machine on Earth. It's not a new dam or a flashy bridge, it's a giant laser fusion lab aiming to bottle star power. If it works, we're talking near-limitless, carbon-free energy with zero reliance on oil, coal, or cloudy weather forecasts. While other countries are still figuring out the basics, China seems to have hit fast forward, and the rest of the world is nervously peeking over the fence. What is nuclear fusion, and why does it matter? Nuclear fusion is the process that powers stars, including our Sun. It works by fusing two light atomic nuclei, typically isotopes of hydrogen, under extreme pressure and temperature. When they combine, they form a heavier nucleus and release an enormous amount of energy. The appeal of fusion lies in its potential to generate vast energy without the drawbacks of current power sources. It produces no greenhouse gas emissions, no long-lived radioactive waste, and carries no risk of meltdown. Moreover, the fuel required for fusion, primarily deuterium and tritium, is relatively abundant and accessible. In contrast to fusion, traditional nuclear power plants use fission, which splits large atoms like uranium. Fission produces dangerous radioactive byproducts, and if cooling systems fail, it can result in catastrophic meltdowns. Fusion, on the other hand, offers a clean and safe alternative that could power entire cities with minimal environmental footprint. However, as ideal as fusion energy sounds, the real challenge lies in achieving and sustaining it under controlled conditions on Earth, a task scientists have been struggling with for decades. A long history of ambition and frustration. Efforts to control nuclear fusion began as early as the 1950s, driven largely by military research in the United States and the Soviet Union. Originally tied to the development of thermonuclear weapons, the idea of peaceful fusion energy soon gained attention. Over time, the vision shifted from weaponry to clean power generation. This transition led to the construction of complex machines called tokamaks, designed to achieve magnetic confinement fusion. Tokamaks work by heating hydrogen gas into plasma, a state of matter so hot that electrons are stripped from atoms, and using powerful magnets to trap the plasma long enough for fusion reactions to occur. These machines must reach temperatures exceeding 100 million degrees Celsius to initiate fusion. Despite many breakthroughs, no tokamak has yet produced more energy than it consumes in a way that is scalable for commercial use. Projects like International Thermonuclear Experimental Reactor in France, a collaborative effort among over 30 nations, including China, the US, and the European Union, continue to explore magnetic confinement, but the first results are not expected until the 2030s. The laser alternative. While most fusion research has focused on magnetic confinement, another promising method exists: inertial confinement fusion, or ICF. Unlike tokamaks, which use magnets, ICF relies on an entirely different approach: laser compression. This method involves firing dozens or even hundreds of high-powered lasers at a tiny pellet of fusion fuel, causing it to implode. This implosion must occur symmetrically and with immense precision, creating the conditions necessary for the atomic nuclei inside to overcome their natural repulsion and fuse. The National Ignition Facility in California is the most well-known example of this technology. After years of trial and error, National Ignition Facility made history in December 2022 by achieving ignition, the point at which a fusion reaction released more energy than the fuel absorbed. While this did not mean the system as a whole produced a net energy gain, it marked a critical milestone. For the first time, a laboratory-scale fusion reaction produced more energy than it consumed at the core reaction level, demonstrating that the principle works. China enters the race with unprecedented speed. After the US breakthrough, China rapidly advanced its own fusion efforts. A major new research center near Mianyang, home to the China Academy of Engineering Physics, is nearing completion. Satellite imagery shows 4 massive laser bays aimed at a central chamber, likely for synchronized compression of a tiny fuel pellet. While officially focused on energy, The facility may also serve military purposes. Laser fusion can simulate nuclear warhead performance without live testing, making the program a strategic tool as well as a scientific one. China's broader fusion strategy. This is not China's first venture into fusion. The country has already developed and operated several magnetic fusion reactors, including the East Tokamak, nicknamed the Artificial Sun. In 2021, EZ broke records by sustaining plasma at 160 million degrees Celsius for over 100 seconds. Another major project, the HL2 and Tokamak, located in Chengdu, is helping China test new configurations and operational techniques. What sets the new laser facility apart is its potential to leap ahead of traditional magnetic designs. China is now exploring both branches of fusion, magnetic and inertial, with serious intent. By committing to multiple paths at once, China increases its chances of being first to commercial-scale success. The rapid construction timeline of the Mianyang site suggests that China is not just experimenting, it is racing. The science behind direct drive fusion. Unlike National Ignition Facility in direct drive fusion, which transfers laser energy via a surrounding structure, China is pursuing direct drive fusion, firing lasers directly at the fuel pellet. This reduces energy loss, but requires extreme precision. All lasers must fire simultaneously, and the pellet must be perfectly uniform. Even slight flaws can cause failure, making it a major technical challenge. If successful, direct drive fusion could offer faster energy output, simpler reactors, and lower costs. Experts note that construction at Mianyang began only recently, but is already nearing completion, with testing possibly starting within 2 to 3 years, potentially placing China at the forefront of fusion development. Why fusion matters in today's energy crisis. The world's current energy system is fragile, pollutive, and uneven. Fossil fuels remain dominant, contributing to climate change and geopolitical tension. Solar and wind power have grown rapidly but are inherently intermittent, dependent on weather and daylight. Energy storage technologies like batteries offer some relief but are expensive and limited in capacity. Fusion energy could resolve these problems in one stroke. The fuels it requires, such as deuterium, extracted from seawater, and tritium, which can be produced from lithium, are widely available. Fusion does not emit greenhouse gases, avoids long-term waste problems, and carries no risk of catastrophic failure. Most importantly, it has the potential to generate massive amounts of energy from a very small amount of fuel. Just 1 kilogram of fusion fuel could provide enough electricity to power a large U.S. city for an entire day. The implications for climate policy, economic stability, and global energy independence are profound. The remaining obstacles. Despite the promise, commercial fusion is still not here. Achieving ignition is only the first step. For fusion to be viable at an industrial level, it must be repeatable, efficient, and continuous. Current systems operate on a single-shot basis, requiring enormous infrastructure for each brief reaction. To power a grid, reactors would need to perform multiple successful reactions every second without failure. Additionally, laser fusion demands the construction of ultra-high precision components, from mirrors to fuel pellets to cooling systems, that all must work in perfect harmony. Even microscopic errors can ruin a reaction. For now, these challenges keep fusion in the realm of laboratory science, but every step forward reduces the technological gap between theory and reality. A race with global implications. Fusion energy isn't just about powering homes and factories. It's a strategic asset. The nation that first masters scalable fusion will lead the next global energy revolution, setting the rules for new industries, supply chains, and scientific standards. Control over fusion means control over patents, reactor designs, fuel processing technologies, and the infrastructure to export them globally. While fossil fuels can be embargoed and traded, fusion fuels like deuterium and lithium are much harder to monopolize. What truly matters is who has the capability to harness them efficiently. That's why countries like the United States, Japan, and the European Union are also racing to scale up their fusion programs. But China's aggressive development pace is shifting the momentum. The tipping point. If China's laser fusion facility achieves consistent ignition and begins to approach net energy gain, it could represent a turning point. No longer just a physics experiment, fusion could move into the realm of real-world application. That would mean a new era of abundant, clean, and stable energy. Electricity prices could drop dramatically. Emissions could plummet. Entire sectors, such as transportation, industry, and computing could run on zero-carbon power. The geopolitical impact would be just as significant. Energy independence would be within reach for any country with the right infrastructure. Conflicts over oil and gas could become relics of the past, and the balance of global power could shift toward nations that dominate fusion innovation. And that wraps up our deep dive into China's bold leap into laser fusion and what it could mean for the future of clean energy. Do you think fusion will finally deliver on its promise, or is it still decades away? Let us know your thoughts in the comments below. We'd love to hear what you think. If you found this video interesting or learned something new, don't forget to give it a thumbs up and subscribe to the channel.